Hello everybody. So this is a physics video about seatbelts and car crashes. And just like I do normally in class, I do want to mention that if you are going to be uncomfortable watching a bunch of car crashes, just let me know. In this case, email me and I will provide you some alternate ways to learn about this stuff. But you've got to let me know right away as soon as you see this video. Don't wait until right before the deadline, okay? All right. But all the videos that you see in here that are in this playlist, if you happen to go to the playlist that I have on my YouTube channel, they are all either crash test dummies in real crashes or actors that are not in real crashes. There are no actual real crashes with people in the vehicle. Okay, so they're all crash test dummies, or they're just actors and it's a simulated type of thing, you know, with special effects, that type of deal. Okay, all right. So we're going to talk about seatbelts today, okay? And hopefully you already wear your seatbelt, okay? But by the end of your assignment today, if you don't wear your seatbelt, I will claim that you are either have an irrational fear or you're dumb. And by dumb, I don't mean that you're not intelligent. I mean that you are making dumb decisions with your life, okay? You should buckle up. But this is the physics behind why we should buckle up. If I was really trying to change your behaviors, if I thought you weren't wearing your seatbelt, the best way to probably do that is with an emotional plea, which is where we get those assemblies where people are crying and stuff because of how emotional they are. That's the real way a lot of times you change people's behaviors. But you're sitting in a physics class, so for some reason you aren't buckled up, or you know somebody that doesn't buckle up, maybe this will change your behavior because of the logical part of your brain. You'll be like, oh yeah, it makes sense, okay? All right, so now let's go ahead and take a look at a car crash here. So this is with and without a seatbelt. Oh, and we're going to ignore the airbag. The airbag does work in conjunction with the seatbelt. When people engineer the vehicles for the airbag to deploy, you're supposed to have the seatbelt on. So don't think that the airbag by itself is going to protect you in a crash. You do need to also be in that certain spot where the seatbelt's supposed to be. And also I should mention, in case you're not aware of this, at some point you've had the experience in your vehicle of the seatbelt locking up, like when you went around a turn a little too fast, or maybe you had just stepped on the brakes or just started your car or whatever and stepped on the gas. You're like, oh, my seatbelt's locked up. There's actually an accelerometer, and it could just be a mechanical device in the seatbelt itself, like in the wall of your vehicle. You can look up there are different designs for this. Usually it's a real simple thing. And basically, if the acceleration gets big enough, the seatbelt locks. And that's what's going to be happening here with the seatbelts. You can assume that they've locked and that there's a certain spot where you can't go any further with the seatbelt. Okay, here we go. So here comes our car crash. Our crash test dummy slowed way down. And here's the zoomed in shot of that. And the crash test dummy, as you would expect, keeps going forward and smashes into the windshield, actually busts out the windshield with the head, and also hits the steering column of the vehicle. So it keeps going forward and then hits that stuff. All right, so that's without the seatbelt. Here is with the seatbelt. And the crash test dummy obviously goes forward, hits the airbag, which we're not worried about. The seatbelt is locked, okay? And that occurs. Here's the zoomed in view of this. Still a very bad crash. Here's the zoomed in view. Okay. I mean, it was bad enough that we got an imprint from the paint on the airbag there, but that is with the seatbelt. We're not worried about the airbag. It works in conjunction with the seatbelt. Here they are side by side. And looking at these two, it doesn't look that different, right? Okay. But as we're going to talk about in a minute, there is enough of a difference between these two crashes to save lives. All right, so go ahead and continue. All right, now the question is, why is this one better than this one? Minus the fact that this guy probably got whiplash. This guy's probably dead. This guy probably has whiplash, okay? I don't know what speed this was at and how survivable this head-on crash was, but you want to be this one. You don't want to be that one. Whiplash is better than serious internal organ injuries and stuff like that, okay? So the question is why, okay? So when we're thinking about this question, we want to frame it in the context of fat app, okay? So we want to think about this in terms of fat app. So F delta T equals the change in momentum, where F is the average force experienced on the person during the collision, T is the time of the collision, and delta P is the change in momentum of the person that's in the car crash, okay? So in both, I'm going to help you with this, okay? And then I'll ask you to think about what might be different and why about the car, okay? But with regards to the change in momentum, in both cases, the person in the car is like going this way, okay? Yeah, they got a car around them, sure, okay? But in both cases, they're going to hit this wall and come to a stop. So if you're going with or without the seatbelt, if you're going to hit a wall, okay, and you're going 60 miles per hour, and then you come to a stop, your change in momentum is going to be the same with or without the seatbelt. So if your seatbelt's not on, your mass stays the same, and you're going to go from 60 miles per hour to 0. If you have the seatbelt on, again, mass stays the same, you're going to go from 60 miles per hour to 0. So in both cases, with or without the seatbelt, this number, which will be a large number, okay, positive or negative, depending on which way you call positive in the problem. But there will be a large number here, okay, for our change in momentum. Huge number if you're in a head-on crash, okay? So the question is, why is the moment with the seatbelt more survivable, more likely to survive, okay? So think about over here, the average force and the delta time. So go ahead and see if you can think about what might be different about with the seatbelt that helps you do okay, all right? So go ahead and pause the video for just a moment. Welcome back. So hopefully you thought, hey, there must be something where this average force is less with the seatbelt, which just algebraically means the time of the crash for you in the vehicle must be bigger when you're wearing the seatbelt, okay? Now the question is why? Why is the time bigger when you have the seatbelt on? So why is the time bigger when you have the seatbelt on? Let's go back and take a look at that video again, okay? These side by side here. And I'll give you a huge hint, okay? In this one, you're attached to the car. In this one, you're not. You will hit the steering column and the dash, okay? So this one, you're attached to the car. Look at what the car does. Think about why is the time for you to come to a stop a little bit, we're talking probably tenths of a second, bigger when you're wearing your seatbelt. Go ahead and pause. Welcome back. Hopefully you came up with some guess, but if you didn't, don't feel too bad. Usually when we have group discussions, I got to kind of like walk around and prod people a little bit and you know, give some hints and stuff like that. But it has to do with the fact that the car squishes, okay? In fact, the marketing department at some point got a hold of what the engineers were doing. They started to call these crumple zones, okay? And making it like a safety feature, okay? Modern cars, and this isn't even that modern a car, but modern cars are designed to squish. They're designed to accordion, okay? They're designed to break inward, okay, like this, squishing up. What you don't want in a crash is for you to hit a wall or something or another car, and your car looks great after the crash. If it's a high-speed crash, that's a bad thing. So if you're driving around in some old truck or car from the 70s, it's not very safe if you get in a wreck, okay? For the very reason that they didn't used to design cars to squish as well as they do now, okay? So if you're attached to the car, you come to a stop with the car. And all that squishing of the front of the car takes time. That extra little bit of time decreases your average force. Whereas in this case, okay, where you're not buckled up, you keep flying forward and you hit the steering column, okay, which doesn't squish real well, or the windshield, which doesn't squish real well. Or maybe you eject from the vehicle. And if you eject from the vehicle and you hit another car, a curb, or a tree, again, those things don't squish real well. You will come to a stop in a hurry. So it's all about those extra couple tenths of a second because you're attached to the car and the car squishes. And the airbag helps with that too, but we're really just talking about the seatbelt right now, okay? Airbag is the same ideas, okay? All right, so now let's go ahead, just go back here for a second to the OneNote just to review that idea, okay? So we have a couple extra tenths of a second here, maybe a little bit more, maybe a little bit less, depending on the kind of crash, okay? We have just a little bit of extra time here, but even going from like 0.1 to 0.2 seconds, that's a doubling of this time, which will cut this force in half, meaning you want that. You want the average force on you during the collision to be less. That is a good thing in terms of magnitude. I'm talking about magnitude, the force here being less, okay? So that's what it's all about, okay? You're changing momentum, you can't help that. You're gonna come to a stop no matter what. The question is, how long does it take? So this is why sometimes you will see car crashes that are spectacular in races and the driver gets out and walks away. So have you ever seen one of those Formula One cars, or sometimes NASCAR, this happens in NASCAR as well, where the car will go up in the air and flip and all the parts will fly off and the thing will roll and roll and roll and roll, and then the driver walks out and they're like, oh, he just has minor cuts and bruises. That's because it took him a long time to come to a stop. The really scary crashes are the ones where a car will hit a wall and then it won't be spectacular at all. It'll just be like bam, like that. And those are the ones that unfortunately often kill race car drivers. The ones where they hit a wall and they come to a stop in a hurry. The car might not look too bad and things aren't flying through the air necessarily. But it is, you come to a stop in a hurry, this number is a lot smaller, that number is going to be a lot bigger. This change in momentum, okay, some big number over here, but it'll be the same no matter what you do with what you're hitting and whether or not you have your seatbelt on, okay? All right, so now let's go ahead and go back to our videos. Go back to our videos here, okay? Just want to show you a couple more. Oh, no, I don't want to change the playlist order, okay? Now, sometimes students will tell me that they, now this is going to be with a crash test dummy child, but sometimes students will tell me or I ask, and they will tell me that they put their book bag on the seat next to them, okay? Now, if all you have in your book bag is your laptop, you're probably okay. If your book bag has a physics book and an AP Calc book and your world history book or whatever, and it's like 10 or 15 pounds, that can actually hurt you a lot in a car crash. You really should put those things down where people put their feet, okay? Or better yet, in the trunk if you have one, trunk of your vehicle. Okay? I mean, I guess you could buckle your book bag in as well. That's a little weird. I would just put it down by the feet. Anything over a couple pounds can be really dangerous. This also includes other passengers, okay? Because you slam on the brakes and they're not buckled up. You might be like, I'm buckled up, I'm doing the right thing, I'm safe. The other people in the car can hurt you. All right, so let's go ahead and let this play. Now the front seat's taken out, but this just gives you an idea that objects will keep going forward, okay? Here is the crash test dummy buckled up. Here's the crash test dummy not buckled up. All right, so if we take a look at this one, here's the person buckled up in the front seat with the airbag. At this point, they are probably okay. All right, they're probably okay. The airbag is deployed. Problem is, person in the back seat is not buckled up, okay? So imagine someone like me, like 230 pounds, sitting behind you in the back seat there for a head-on crash. And I come flying forward at 40, 50, 60 miles per hour, okay? Not only do I hit the seat, but I squish the person in front of me into the steering column. This person might say, oh, hey, I don't care if I get hurt in a car crash. I'm willing to take the risk. That's when you got to realize that if you're in the car with them, say, hey, it's not just your life you're putting on the line, it's the other people's as well, okay? And then depending on who the person is, maybe make a joke about it to get them to buckle up if you're the driver. I mean, you're in a tough spot if it's your parent or guardian and they won't buckle up. But I don't drive anywhere with other people in the vehicle unless they buckle up, okay? If I'm the driver, I'm not going anywhere unless everybody's buckled up because those other people can hurt other people in the vehicle. Now, someone might be saying, what about my pets? Well, let's assume for a minute the horrible thing that you don't care about your pet. Well, if you don't care about your pet and you get in a wreck, okay, fine. The issue becomes the fact that the pet, if it's something over a couple pounds, okay, imagine getting hit in the head in baseball going 60 miles per hour, and now instead of that, it's a 50-pound dog or a couple pound cat or whatever. That can actually seriously hurt you. Now, I'm going to assume that most of you, if you have pets, you care about your pets. And if you let them run around in your back seat or whatever, and you're on some dirt road in the middle of nowhere with no trees along the side of the road and you're going 15 miles per hour or whatever, sure, okay? If you're driving in traffic, no, okay? That if you care about your pet should be restrained. So some people are like, what do I do, buckle it in, okay? Well, probably not, unless you've got some like trained chimpanzee that will listen and like you can buckle it in like a small child or whatever, okay? Probably for dogs, you should probably have, or you should have, some sort of a car carrier that you can secure to the floor, the bed of the truck, the back seat. Some of them strap in to the seat belts and stuff like that. I've even been told by students for small dogs, they do make little things you put the dog in and you buckle it in and everything. You do need to restrain your pets. They don't like it, okay? But if you care about your pet, you don't want them bouncing all over the car like a pinball when you get in a wreck, hitting all sorts of really hard surfaces. You want to attach them to the car just like you'll be attached to the car. And then if it's a cage type scenario, hopefully some padding there as well. But you really don't want them flying all over the car. Okay. Now, sometimes people say, well, what about if I can just hold my pet? You did a problem the other day where you found out that it required, I forget how many, it's the equivalent of like, between 10 and 20 people to just like, if you had your hands up in the air and you snapped your fingers, it's the equivalent of having like 10 or 20 people in a box all of a sudden. You cannot stop yourself from going forward in a crash. Also, you cannot stop your pet from going forward, which leads me to this. Now, I don't see people doing this with babies anymore, but I still see people doing it with pets. Here's the slow-mo. neither person's buckled up, but even if you're buckled up, you can imagine that crash test dummy representing the child or the pet will fly out of your hands. You will not be able to keep the object from leaving your hands. Okay, this is also why the reaction, if you're about to get in a crash, should not be throwing out your arms. Okay, there are times when maybe that's good, okay, because of protecting your vital organs or whatever. If you're about to fall down a hill or something, you'd rather break both arms and both wrists than your head. Okay, but the reaction if you're about to get in a crash in a car to go like this is not a good one. Okay, because you've got the seatbelt on, you're not gonna be able to stop yourself going forward. The seatbelt will. If you can actually reach the dash, all that's gonna happen is you're gonna have extra damage to both of your arms. My mother, who is very short, she's like 5 feet tall. In fact, she might be under 5 feet tall now. Whenever I drive around, I drive very safe, at most 5 miles per hour above the speed limit, but she lives in a small town. She's not used to traffic necessarily or somebody else driving. And every time I go around a corner or I pass somebody, even if I'm going exactly the speed limit and the other person's going like 10 below, a lot of times she'll go like this. Now, luckily, she cannot reach the dash in my current vehicle, but even because of the airbag, because she's so short, but even because of the airbag, that is a bad thing to do, throwing out your arms and locking your elbows. That is, the idea of bracing for impact by doing that in a car, really bad idea. Really bad idea, okay? So don't do that. If you have the presence of mind right before you're about to get in a wreck, nobody does this, but if you're having the presence of mind right before you get wrecked, you'd really want to just try to relax if there's nothing you can do about it. Just take a deep breath and try to relax, and you'll probably have slightly less injuries as a result. Again, the seatbelt and the airbag should be doing their job though, okay? Now, let's go ahead and go to, I keep wanting to do that. Let's go ahead and go to one more thing here. So sometimes, by the way, this channel is called Zero Fatalities. I don't know any other videos that are on here. The title of this video is not Zero Fatalities. This would be multiple fatalities if this was the kind of crash you had. So you've probably been told stories where people eject from cars and they survive. And that can happen. Okay, you fall off a motorcycle, you get ejected from a Jeep, or you get thrown out the window, you bust through the window. And yes, if you are very lucky and you slide to a stop along a long distance, similar to those cars rolling in Formula One, okay, flipping through the air, whatever, it takes a long time to come to a stop, you could be okay. The issue is, a lot of times on roads, there are other cars, there are curbs, there are trees, light poles. And none of those things, if you hit them with your human body, are going to give a whole lot. They're going to bring you to a stop in a hurry, which is bad news. Okay? So here is a high-speed rollover where none of the crash test dummies are buckled up. Here we go. All right, crash test dummies are ejecting, okay? And I should mention this guy that's going to go up off the screen right now. A fall from 6 feet onto your head onto concrete can actually kill you, okay, if you hit in the correct way. So this guy's going to be falling from way higher than 6 feet. Falls are really dangerous. That's why most of us are afraid of heights, probably. I don't know. Talk to your biology teachers. All right, now. This guy is kind of rolling along. The issue is going to become, what if there were other vehicles? Okay, a couple more going up in the air. And then also, I think he gets rolled by the actual vehicle he was ejected from. Again, these are all crash test dummies. Had a slight recording issue, filled up my iPad. So this is a continuation of that video you just saw. I'm just going to put them together in the same video. If you're wondering, things look a little different, that's what happened. All right, so I believe we were talking about that guy was going to get rolled over. Let's go ahead and advance the video here. But suffice to say, this wreck, for these people that are ejected up high, is going to be really bad. Even if you just fell from that height, it could be catastrophic. And then also, there'd be other vehicles here. There could be trees. A shoe has flown off because of the violence of this. There's that guy that left earlier, landed right on his head. This is not zero fatalities. This would be multiple fatalities. For this car crash, if this happened on a busy road. Even if it didn't, a couple of these people are certainly, if not killed, seriously injured, life-changing injuries. Okay, now the other videos on this playlist on collisions and momentum, you're welcome to watch them. Eventually, we will watch some of these other ones. They'll be in a playlist you'll watch eventually that aren't car crash ones. But the car crash ones are generally at the beginning if you're looking for that. Let's go ahead and address the rational fears. So the 2 irrational fears, I'll do this quickly. I'm not going to do the extended version I do in class. Just real quick. People are worried they're going to drown, or the fire in their car, if they get in a wreck, is going, the car is going to blow up, okay, or they're not going to be able to get out in time because of the fire that might develop in a car after a crash, okay? So for the drowning one, most bodies of water are below roads, okay, highways. They're elevated, right? Okay, they're up high, okay? So you got the body of water down below. So typically, if you're going to crash into a body of water, you are going to roll down a hill. And if you roll down the hill, you're going to get a lot of injuries if you're not buckled up, which means you won't be able to swim to safety. Sometimes people are like, oh, but as soon as I hit the water, I want to be able to get out. You are not going to be able to leave your vehicle until the car completely fills with water. Because if you try to open the car door, that water out there, the pressure difference, you're not going to be able to open it. And you're like, oh, roll down the window. Water will rush in the window. So you'll have plenty of time to unbuckle your seatbelt. And then once the car is full of water, you open the door. The biggest thing, if you find yourself ever in a car that's filling with water when this happens, is you got to keep presence of mind to swim upward. And it's tougher than it sounds. If you're in some murky water and your vehicle has rolled into it, you are going to be disoriented. The military trains for this. They practice on helicopters with rolling it into a pool, and then the guy's got to try to get out. And it's going to be a little tougher from a helicopter if you're buckled in the back. But a lot of them don't make it on their first attempt. Now, when I say they don't make it, a scuba diver comes in and gives them oxygen and helps them out, right? But they wouldn't have made it if that was the real world. So the key thing is when you open the door, let some bubbles out, okay? Breathe out a little bit, and obviously don't breathe in. See which way the bubbles go, and make sure you're swimming up because it's really easy to get disoriented. All right, so that's the first irrational fear. And I say irrational because if you're not buckled up, you're not going to be able to swim to safety anyway. But if you're really afraid of drowning, I understand. You just got to try to convince your brain that it's a good idea to buckle up despite your fear of drowning, okay? The second one of these is the car burning. And think for a moment if you've seen cars with flames or smoke coming out of them before. The answer for many of you may be yes. I've seen several cars on fire in my lifetime, not any that I've been in. And then ask yourself the next question, did any of them go and blow up like a Michael Bay movie? And unless someone was trying to do it, my guess is the answer is no. You've never seen a car burning or having smoke come out of your daily life that then just went boom a moment later, okay? Cars are not engineered to explode, okay? So if there's a little bit of fire somewhere in the car, it's not supposed to go kaboom and blow up, okay? That would be horrible engineering. So they are designed not to have that happen. Is it possible? Sure. Is it likely? No. And if you're in a car crash that is bad enough to the point where your vehicle is now in flames, if you weren't buckled up, again, you're probably already seriously hurt or dead in the car. You need to be buckled up so that you can unbuckle and then get out of the car that's burning. You should have plenty of time if the car is on fire. I mean, don't sit there for a long time. Once it's safe to leave the vehicle in terms of traffic and stuff, get out of the vehicle if there's smoke or if it's on fire. But it's not going to blow up like it does. It's very unlikely it's going to blow up like it does in the movies. Okay? That's special effects. Those are cars designed to do that. Or there's just CGI, right? So now those are the two irrational fears. The next thing we have to do is for your actual thing you got to turn in. Now I already did this, so I'm just going to zoom in to reduce our view here a little bit. I already did this for the first take of this video and filled up my storage. So round 2 here. So what you're going to do is, okay, you are going to submit just a little bit of work to me, okay, for a sample problem with realistic numbers for a car crash and why seatbelts are a good idea. Okay, so a reminder, the whole idea why they're a good idea is because of that fact that the front of the car squishes, which takes time, and then you're attached to the car. So however long it takes the car to come to a stop, it'll take you to come to a stop. And that extra tenth of a second can mean the difference between life and death. Because your change in momentum is going to be the same, increase the time, decrease the average force. Okay, so that's the idea of that. Now, for the sample problem, we're going to actually put numbers to this. Okay? So you're going to have, and if you don't want to pretend it's you, pretend it's a crash test dummy, that's fine, okay? So here's person in the car, or you in the car, moving to the right, okay? And you'll draw that picture, okay? You'll draw that picture. And then we're going to call right positive. So put on your paper or your OneNote or whatever, right's positive. And then you need to make up the mass of the person or the mass of you. So if this was me, it'd probably be like, I don't know, 110 kilograms, 115, I don't know. I'm like 240 pounds. I don't know what that is in kilograms. So what should you do to figure out your mass in kilograms? Just use Google. So go into, open up a Google search and just type, whatever you are, 150 pounds equals, and then, kg, okay? And it'll spit out an answer. If it doesn't, use an online converter of some sort and just get an answer. You don't have to do any actual calculation yourself. Just let the converter do it, the online converter do it. So figure out your mass in kilograms, kg in kilograms, and write that here. So you'll have mass of you equals a certain number of kilograms. Your mass of person or crash system equals how many kilograms. For V final, in all of your sample problems that you guys are doing, you're going to have the car come to a stop. Okay, we're all going to assume that if we hit a wall, we will come to a stop. So V final, no matter what else you're doing, will be 0. So everybody use V final of 0. And then for the initial velocity, for V naught, make up a number that is reasonable in meters per second. So this mass of the person needs to be in kilograms. The initial velocity needs to be in meters per second. So what do? Well, if you want a 50 mile per hour car crash, again, go to Google, type in 50 miles per hour equals, and then M divided by S, see what it spits out if you want it to be 50 mile per hour crash. Okay, so write all that stuff at the top of the problem. All right, then what you're gonna do is we're gonna have this is like a two-part problem. There's gonna be with the seatbelt, is this one, the first one, and then without the seatbelt. And you'll write with and without. The W with the slash means with, and then the T equals is where we'll put the time for these two different problems, okay? So the key thing is when you make up the time with the seatbelt, it needs to be bigger than the time without the seatbelt. In terms of what's reasonable, I would say the time should be under a second, but probably not much smaller than 0.05 seconds. I am guessing that most of the kind of crashes that would be hitting a wall like this would take a tenth or a couple tenths of a second. But that is me just guessing. If you're really interested in this and you want to go out and do some research and see how long car crashes take to come to a stop with various objects, cars, walls, whatever it might be, you're welcome to do that. If you do that and you want a little bonus, just send me the links for what you found and tell me what you found out. Okay, but otherwise, maybe use for with the seatbelt, maybe use 0.2, and then without, maybe use something like 0.1. Okay, seconds. All right, now you'll write this line. That's our impulse momentum theorem, our FAT app. Okay, don't forget to write the AVG for average. So don't forget to write this for the average force during the collision. Okay, T is the time of the collision, and delta P, remember, is the change in momentum. We're hitting a wall. There will be a large change in momentum. Okay, there's going to be a big change in momentum. Change in momentum. So then next thing, I've expanded this out. So you can, if you're confused by this next line, feel free to look back at the notes from yesterday. But remember, delta P is the change in momentum, which is mv final minus mv initial. So that mass times that velocity at the end, minus that mass times velocity at the beginning. Or factor out an m. M, it stays the same. M times V final minus V naught. And write that for both of them. And then you'll substitute in, okay? Be careful on your signs. Your V initial should be positive. So when you take 0 minus a positive, you will get a negative for the change in momentum and a negative for the average force. That should make sense because if you're moving to the right in the vehicle, and you're in a car crash, there's going to be a big average force on you to the left because it slows you down and brings you to a stop. So there's got to be an acceleration to the left, which means there's a force to the left. Okay, so it's all consistent with what we learned before. Okay. All right, so then the next line you write here, plug in your time, plug in the mass, plug in the two values from up above, and then solve for F average. Do the same thing over here. At the end, hopefully the F average with the seatbelt is less than the average force without the seatbelt. All right, if you have any questions or run into any problems, let me know. And hopefully you guys buckle up. And again, if there's anything over a couple pounds, including your book bag, pets, other people, it really should be secured or down low. This also includes anything with like a sharp edge. Like if you have a golf umbrella, the ends of them are metal, they're rounded, but they're metal. Golf umbrellas can have gone right through seats and out the person on the other side. It's very rare, but there have been a couple of reported cases of that. So if you've got something that's sharp, it should also be down low. I don't know if I mentioned this already, but when you pack a car, you kind of already automatically do this if you're packing for a big trip. But if you got to pack stuff up really high in the car, the stuff that should go on the top should be the lightest softest, least pointy items should be up top. You want all the stuff that could seriously hurt you down low because your vital organs are up here, right? Your vital organs are not down in your ankles and your knees and stuff like that. So you want those heavy items or sharp items to be down low in your vehicle when you're traveling. And please, 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 if your book bag weighs over a couple pounds, put it down where someone would normally put their feet or in the trunk of the vehicle, because your book bag with several books in it and a laptop and all that, if it's over a couple pounds, it actually could seriously hurt you and cause life-changing injuries in a crash. It could. All right. I think that was it. Have a good day.